organizing committee for allowing me to present the first results of my master's thesis and a bit of my PhD, the beginning of my PhD on the interaction between type 1 X-ray bursts and accretion disks, so the kHz QP angle. So first, what were the motivations of my work? So as you know, type 1 X-ray bursts correspond to the thermonuclear explosion of the surface of the neutron star, and during these events a wide range of luminosities is explored by the central source, and a considerable amount of energies is released, and some of it is delivered by to the accretion disk, which could have an influence on it. And so therefore I think that type 1 X-ray bursts are a unique opportunity to study the inner parts of low-mass X-ray binaries. So this problematic has already been studied through spectral analysis, notably in 2004, Ballantyne and Strohmeyer during a superburst of 4U 1820 claimed evidence of a growing inner radius of the accretion disk during the burst emission, and more recently Worpel et al. Claimed evidence of an accretion rate enhancement during type 1 X-ray bursts. So to do so, they proposed a new method to fit X-ray spectra during type 1 X-ray bursts. So instead of simply fitting a black body model over a fixed persistent emission, they add this scale factor on the persistent spectra, allowing the persistent emission to be enhanced during the burst. And what they found is that during type 1 X-ray bursts, FA value superior to 1 are statistically favored, and they claim this is an evidence of accretion rate enhancement during type 1 X-ray bursts. And these results may have been also seen by Inzant in an XMN Chandra observation recently. In terms of modeling, Walker in '92 in fact predicted this accretion rate enhancement and also this depletion. So it did the modeling of the evolution of a thin relativistic and irradiated accretion disk, and he found a significant influence of radiation torque on the accretion flow, leading to this accretion rate enhancement and disk depletion. Ballantyne and Everett, following the observation of the superburst of 1820, also studied several effects during this episode, like accretion disk heating, disk depletion, and outflows. So why now did I use kHz QPOs to try to tackle this issue? Well, as we have seen during this conference, there's no consensus yet on the origin of kHz QPOs. However, some features are commonly accepted, and notably the fact that the upper kHz QPO frequency is commensurable with the orbital frequency at around 10 Schwarzschild gravitational radii, or epicyclic frequency, tend to let us think that this emission is produced in the most inner parts of the system. And also spectral analysis has contributed us to know that these emissions have other spectra than the disk, and this will become handy just now. And so I believe that kHz QPO are a probe of matter, the behavioral matter in the inner parts of the system, parts of the systems that can be affected by the emission of the type 1 X-ray bursts. So the data set that I used was XTE PCA data of 2 low-mass X-ray binaries with neutron star that are 4U 1636 and 4U 1608 that are known to be extensive bursters, but also that emit frequent, strong, and narrow lower kilohertz QPO that can be detected on the time scales of the type 1 extra burst, that is to say, in around a few tens of seconds. Well, as the burst emission is rather soft, and because the spectrum of kilohertz QPO is harder, I chose to get rid of some of the burst emission and to restrict my study between 6 and 50 keV, and with high timing resolution data. So I selected the events in these two sources where there were strong kilohertz QPO detectable before and after the burst onset, and this gave you 10 events for 1636 and 4 bursts for 1608. So the first step of my study was to compute dynamical Lane normalized power density spectra, and this is what I show here in this plot. So as a function of time, I represent in false color the power distribution as a function of frequency, and you see here and here very clearly the lower QPO kilohertz signal that is detected, and you notice here that the QPO is not detectable. In fact, this is simply due to the fact that the burst emission is not modulated at the QPO frequency, and therefore you have a big increase of the noise level, leading to a smaller detectability of this signal. And then the QPO frequency returns at the same. The QPO returns at the same frequency, and there is in this case no apparent modification of the signal. Well, so this is true for most of the events, but for 3 different bursts in 1636, burst number 4, 22, and 23 in the Galloway classification, you see that there is a longer disappearance or undetectability of the kilohertz QPO signal, even though the count rate has reached practically its persistent level again, as you can see. And so I asked myself the question if this was a significant effect. So has the type 1 extra burst done something to the disk or something else preventing the kilohertz QPO to be emitted? Well, the principle of my simulations was to simulate light curves starting from with the hypothesis that the QPO signal was not modified at all. So to do so, I retrieved the QPO parameters in the persistent emission before the burst, and then I simulate persistent light curves using inverse Fourier transform techniques with a QPO that was unmodified. Then I add the burst photons that are Poisson randomized in order to take into account the content noise, and then by adding the two, I get a light curve that would look like as if the QPO was not modified at all. And then I will compare the power excess found in the power density spectrum computed with this light curve with the one found in the data. So in more detail, what I did was for these 3 observations to first determine some time interval that are here represented by these blue vertical lines. So these intervals correspond to the period where the count rate is already quite low, but the QPO signal is still not detectable. So I extract a light curve here, and I do a power density spectrum, and then I look at the maximum power excess level that is present in these frequency bands that envelope the frequency of the QPO emission. And I do exactly the same in the simulations. That is to say that I simulate a light curve in this time interval with these burst profiles, and then I compute a PDS, and I look at the excess that I found in the simulations. And so these are the results of 10,000 simulations per burst. And so the blue histogram here shows the distribution of the excesses found in the simulation. The red arrow shows each time the power excess found in the data, and as you can see, the power excess is way lower than in the simulation in each of these cases. So more precisely, for each burst, no simulation gave a power excess lower than the one found in the data. And in terms of the distance of the red arrow to the mean of the Gaussian fit that is presented here, I found 6.4 sigmas for burst number 4 and around 3.5 sigmas for the two other bursts. So this seems like a significant effect. So now we can compare what we find in these three cases with what is happening, or in fact non-happening, in the others. So here I plot as a function of the burst number the ratio between the RMS level that is measured in the same time interval as used for burst number 22 and 23, which is in fact the same during all the other bursts. So I extract a PDS in this time interval. I fit it with a Lorentzian profile using a maximum likelihood algorithm, and then I plot here the ratio between the RMS level measured in this interval over the RMS level measured in the persistent emission before the burst onset. And as you can see, for most of the observation, this ratio is compatible with the one value, that is to say with no increase of the QPO power or decrease of the QPO power. And for the three bursts that I showed to you before, of course, I could only compute upper limits. And you can see that burst number 4 is rather well outside of the distribution, but the other two are way closer, and so this may mean that the boundary between no modification of the signal and a weakening of or broadening of the signal is somewhat blurry. Well, but can we not go closer to the burst emission? So as you can see here, for all the observations of burst 1608, the behavior of the RMS level is rather stable, and so we can maybe do some stacking of the different PDSs as a function of time in order to increase the signal-to-noise ratio. So to do so, in each of the 5 observations of 1608, I followed the QPO frequency as a function of time with an algorithm similar to the one in Barre et al. 2005, and then I shift all these dynamical PDS to get the stable frequency at a value of 8 that I chose to be 800 Hz, and I get this dynamical power density spectrum as a function of time. So as you can see, the noise level is way lower than before, but here at t equals 0, which corresponds to the burst emission, you still cannot see any QPO signal. So, to investigate this question, I plot here as a function of time the power excess level presents in this frequency band. In fact, the maximum excess level over 4 Hz as a function of time. So each second I compute a 20-second power density spectra. Then I look for the maximum excess over 4 Hz in this frequency band, and this gives me 1 point of the blue curve. Then I shift this time window by 1 second, redo 20-second power density spectra, and this gives me a second point, so on and so on. And you can see here that the level of the power excess as a function of time is compatible with no modification of the signal, because here this green curve has been computed using all the QPO shape that I fitted in the persistent emission of each of the observation. Moreover, if I compute a PDS between 15 and 30 seconds, that is to say around here, I find a highly significant QPO signal that leads us to say that if there is any modification of the QPO signal, this is in around a 20-second interval at maximum. Well, to sum everything up, so 3 birds have been identified in 1636 to present a significant weakening or broadening of the QPO, kHz QPO signal, and all the other birds are compatible with no modification of this signal at all. And in 1608 we could find somewhat an upper limit on the QPO recovery time. So now we can look for a correlation of this discrepancy with burst parameters. So here I plot again this RMS ratio as a function of peak luminosity and burst fluence, and you can see no real correlation with any of these parameters. I tried to do it with also rise and decay time, persistent flux parameter of the burst oscillations, and nothing correlates with the observed behavior. I also performed some spectral analysis to see if there was some evidence of a difference in this observation in the power spectra. So I used Warple's technique, and I found each time similar FA profiles as a function of time. So this accretion rate enhancement as a function of time with around a maximum value of 5 and a return of FA to 1 in around 20 seconds. So, the influence of X-ray burst on accretion disk is quite a difficult problem, but we can try to see what relevant physical processes may be happening here. So first, there may be some accretion rate enhancement as predicted by Walker and may be detected by Warple, and with this FA value that peaks to 5 and returns to 1 in around 20 seconds. But if you do the mean value during 20 seconds, you find around 1.5. And if you take the very simple view that the disk is falling from its inner part to the Newton star, that this should provoke this deflection. If you take some simple Shakura-Sonayev model, this corresponds to the mass contained between 7 and 40 Rg, and so including the region where the QPO emission may be taking place. So we could also think that some heating of the disk could provoke it to puff up and then decrease the coherence of the QPO signal, and each one of these things should be erased on around viscous time scales, that is to say around 100 seconds at 40 Rgs, and around 10 if no this depletion is happening. And there may be also some modification of the comptonization layer, but the fact that we find FA values that are quite high during the burst means that we still find photons at high energies, and which should let us believe that there is still comptonization going on. So very rapidly, what are the possible scenarios that we are observing here? So if FA equals 1 corresponds to the resumption of the accretion flow as before, then this is compatible with no seen modification of the QPO signal, because we detect it around 20 seconds after the burst onset, which is the time when FA reaches 1 again. But as I say, there may be some disk depletion at hand here and a return of the disk in viscous time scale, so this is not compatible anymore, and this becomes compatible with around 100 seconds interruption. So a heating of the disk could also explain why the QPO loses coherence, as is not detected, but it is not clear why it is not systematically the case for bus number 5, for it is longer, and so maybe some other processes may be at hand. So I think this is a new interesting piece of the big picture of the Lomas X-ray binaries, but much still needs to be answered. Thank you very much, and if you have any questions.